Hi guys, let's get started. Okay, so I'm looking at some of these things, and I'm wondering if you guys have submitted the test yet. So let's see. Let's see how many people submitted. Yeah. So we need to submit the test, especially multiple choice. It's so easy. You fill in the you fill in the answers, and then you can see your results, right? So I only have like 2 people submitted, guys. So you didn't do it, you guys? Sorry. Okay. Yeah. So submit it, and then we need your score, because then the score will not be accurate. Like Bronzeman, I don't have yours, right? For example, so we still have a lot of people not submitting the test because we are closer, much closer now to the actual test date. So I want to enforce the testing thing so you guys can do it. Yeah. So just keep a time every week to submit them. It's different when you do it by yourself. Okay. So again, office will continue to nag you guys until you are submitting them. Yeah. For grading. Okay. So if you submit it after class, it's kind of defeat the point, isn't it? Because you already know all the answers, and then you can tell whatever score you want, right? So just yeah. But as long as you're learning these questions, but we need to enforce these policy now. All right. So let's take a look at this multiple choice. And I'm going to try to do the split screen so we can do this. And then if we have time, we can start reviewing. Hopefully, it becomes easier so we can have more times doing more review. But you have to get used to these questions. Remember the 3 response questions, you have those equation sheets available for you. So feel free to use them. Okay, so I'm going to, maybe like this, yeah, okay. So, all right, so let's take a look at the first one. Okay, so, okay, I'm sorry. So, this is not on, let me see. Yeah. No wonder it's so quiet. Okay, so give me a sec. Let me set up the projector. I just have to power it up. That's it. Yeah. Okay. I should be showing up soon. All right. So one of the things that the AP talk about is it's called mass spectrometer. So mass spectrometer is essentially a way for us to figure out if an element has isotopes. Yeah. So like, for example, this question here, it looks hard, but you have to figure out, all right, I got 90, that's the mass, but another isotope is 92, another one is 91 here, and then there's some 94. So this isotope, at least I see there's 4 isotopes for this element, right? So again, every one of those peak is separated by the mass spectrometer because it separates by charge and mass. So I get 90 peak, I get 91, I get 92, I get 94. So they're asking you, what is the average? Because the periodic table have to report the average of these. So you look at the percent abundance. So about 90% is, 50% is about 90, right? All right, and then do you see 92 and 94 have the same? So that's about 93 average. So you have 90 and 93. Wouldn't that be, okay, now you got to look at the periodic table. Yeah. So, excuse me, I have to pull out a periodic table somewhere. Okay. I don't need this. And where's my periodic table? Launch. It's not enough room. So is the periodic table on this one? Let me scroll down to the periodic table. So yours average is somewhere between 90 and 93, but closer to 90, maybe like 92, right? Okay, so periodic table. So always want to have a periodic table handy so that it's hard to memorize all the molar masses, right? So you're looking around 90 something. So I'm looking at around 90 something on the bottom. So I have here, oops, right here. So I have 90, 91, 92, 93. So one of those, right? So if you go back to the question, let me delete this. Back to the question here. So which of the following is the identity of the element? So I would transfer the atomic number over. So let's see. If you look at the first one, okay, Y, and let's look at Y. Yeah. Oh, that took a long time. It popped out again. Oh, it's so stupid. Okay, so let's look at Y. So Y is we're looking at the mass number. I'm sorry. I was looking at atomic number for some reason. So mass number. Sorry. Yeah, this is distracting. So we're looking for the mass number. Okay. So 90, 91. So Y is right here. Is 89. That can't be it, right? Okay. So I would transfer this information over. Oh, this one keep blocking me. So this is 91 something, and this is closer to 93, and this is closer to 96, right? So in order to do this, you would have to, okay, Lord, right here. So it would be B. Okay, ZR is like close to 92. That's the only possible one, right? So you don't have to actually do the calculator. If you want to do this on calculator and find the exact average, it's a little bit harder, but it's 50%, so 0.5 times 90, right? 81, oh, you know, this is not needed. Oh, 15%, so 50, 91, and then 20%, 92, 20%, so plus 20%, 92, and then 20%, like 94, right? So this is a very rough average, but you can just kind of eyeball it. It should be around B. Yeah, so B is the best answer. Okay, MB and TH. If you look at the molar masses, they're way off. So MB and TH. Okay, the molar mass for MB and TH right there. So MB is 93, so that's way too much, way too close. Okay, and TH is just far away. So TH would be all the way down here, 232. That's wrong. So that's pretty easy. First one. So mass spectrometer. That's what it is. Okay. All right. Let's look at number 2. The ideal gas. Describe the property of which is the following. Now, ideal must be nonpolar. So nonpolar, no intermolecular forces, must be as small as possible. So small gas. Yeah. So that's ideal. So describe the property of which of the following. I see the last one because N2 is the only nonpolar. pH3 is trigonal pyramid. Group 5 with 3 things is trigonal pyramid. That's polar. HBr, of course, asymmetrical. There's a dipole, polar. And SO2 is bent. You should memorize it by now. SO2 is bent. All these have polar shapes. So the only nonpolar one is N2. And that's what ideal gas is describing the best here. So the answer is N2. N2 at triple bond, don't forget, is 79% of the air, nitrogen. Yeah. Let's look at number 3. So number 3, at this temperature and pressure, bromine is liquid. We already know that. And chlorine is gas. We know that because these are our favorite halogens, right? We know that halogens are chlorine, so fluorine, chlorine, bromine, and iodine. Oh my goodness, what happened to my chlorine? So chlorine, fluorine, bromine, and iodine. Bromine is a liquid, red-orange, so make sure you memorize it. And iodine is a solid that sublimes into purple vapor. It's a metallic-looking solid that sublimes into purple vapor. The first two are gases, okay? All right, so why? It's because of intermolecular force, right? All these are nonpolar, London dispersion, but the bigger it is, the stronger the intermolecular force, yeah? I think I'm gonna change my, I'm gonna turn off something. Give me a sec. Ink to shape, we're gonna turn it off. All right, so it won't shape it for me automatically. All right, so that's it. So we know it's the intermolecular force. So number 3, the best answer is A. Forces among bromine are stronger. That's true, because it's bigger, more polarizable, stronger the dispersion, right, than chlorine. So A is correct. And B would be wrong, because even though the covalent bond, this covalent bond has nothing to do with intermolecular force. Covalent bond does not determine whether you're solid, liquid, or gas, does not determine your melting boiling point. It does not determine your intermolecular force. Intermolecular force has nothing to do with covalent bond, which is why B, C, D, they're all wrong. They're talking about the covalent bond. We're talking about the intermolecular, not the intramolecular forces. So number 3, the only answer is A. Okay, so intermolecular force, intramolecular force. So if we do a very, very quick review of intermolecular forces, essentially, what do they determine? They determine, number 1, melting and boiling point. Number 2, they determine your heat of fusion, the energy needed to melt, energy needed to vaporize. Heat of fusion, heat of vaporization. So these are controlled by intermolecular force. They determine your viscosity, okay, how viscous something is, viscosity, hello. Okay, so we just started on question number 3 and number 4. They also determine your surface tension, right? So intermolecular forces determines your surface tension and also determines the vapor pressure. The stronger the intermolecular force, the lower, it's harder to vaporize, the lower the vapor pressure. So it has nothing to do with intra forces. So the intra forces do not determine these properties. It's the intermolecular forces. So intermolecular forces are hydrogen bonding, dipole-dipole, dispersion. Those are the 3 most common ones. Okay, so let's look at number 4. Number 4, we're looking for polarity. So that would be the difference in electronegativity. We'll arrange them in order of decreasing. So you have less polar, means non-polar, right? And you have more polar on the left side. So who's the most polar would be A. HF is the most polar, right? And then NF, and then the non-polar one here is FNF. There's 0 difference in electronegativity. So A is a good trend. Okay, so the most polar to the least polar. So the more polar it is, the stronger the intermolecular force in general, right? Okay. All right, so that's number 4. Okay, let's look at number 5. So number 5 here, we have Beer's law, photospectrometry. Remember this one, you put a sample that is colored into a cuvette, the sample holder, and you measure how much light is absorbed. The more light is absorbed, the greater the concentration. The greater the absorbance, the greater the concentration. Essentially, Beer's law says that the absorbance of light due to a sample is directly proportional to the molarity of the sample. It's directly proportional, yeah? And the formula is big A for absorbance, little a, little b, C, right? C for concentration, and A for absorbance, yeah? So this is Beer's law, and where little a and little b are the slope of this line. The slope of this line is little a, little b. And B is actually the width of the sample holder, the width of the cuvette, okay? So B is right here, usually measured in centimeters, is the width of the cuvette, is also the distance light would have to travel through the sample. So, and the little a is a useless constant called molar absorbivity. It's useless because every sample has a different value for A. There's nothing you have to memorize. It's just the slope. So this is directly proportion. So what's going on here for this question? If you look at this one, to determine the amount of Fe in a 100 ml sample of unknown, excess of KSCN, so you might see this quite often, is added to the sample. So the purpose is that you convert Fe3 plus into this guy, FeSCN2+. And it tells you that this is dark red. That's what we need. This is dark red. So as the reaction progresses, you're going to get darker and darker and darker red, which means the absorbance will go higher and higher and higher. And this is why if you look at the chart, the absorbance on the y-axis and the concentration of this dark red product on the x-axis, the more dark red, the more absorbance. Okay, and the product is the dark red, right? So basically, you're monitoring the rate of the reaction. Do you see the slope of this line? Can also be interpreted as the formation of product over time, which is the rate. Yeah, the faster the absorbance increases, the faster the reaction is. So the slope can also be interpreted as rate. So if you were to carry out at a higher temperature, you're going to have a bigger slope. The concentration changes a lot faster. And if you have a shallow slope, that would be a low temperature, right? So this can also be correlated to the rate. Okay, so they give you a lot of information here, right? So let's see what they want. So if the absorbance of the mixture is 0.2 at this particular wavelength, okay, that was chosen for you. So I'm going to go 0.2, extrapolate and go down here. I get 1, 2, 3, 4 times 10 to the negative 5. So at 0.2, so this is number 6, I guess, yeah? Okay, at 0.2 absorbance, A equal to 0.2, my concentration is 4 times 10 to the negative 5 moles per liter. The question is, how many moles were present in a 100 ml? Well, if you know moles per liter, you can find out the moles per 100 ml, right? So if you, this one, you're not supposed to use calculator, right? Multiple choice, there's no calculator. And you convert 100 ml, which is 0.1 liter, from liters to moles. So 4 times 10 to the negative 5 times 0.1, that is 4 times 10 to the negative 6 moles, okay? So the answer is C. Again, from the absorbance, extrapolate to get the concentration. I got 4 times 10 to the negative 5, but that's per liter. You only have 0.1 liter, 1/10 of it. So how many moles do you have? 4 times 10 to the negative 6, and your dimension analysis is there. All right, so that will be one application of that. Let's see what else do they want, yeah? Okay, no more. Okay, so this is the trend in the ionization energy. So we should remember the trend for ionization energy, the one I gave you. So let's look at, this is number 6, before it was number 5, okay? So what is the trend for ionization energy? It increases, if you go up, increases as you go to the right. So ionization energy, abbreviation is IE, increases. What is the reason for increasing across a period? Is because the nuclear charge, okay, increases. So the nucleus becomes stronger and more effective. It's not letting go of the valence electron. And what is the reason for increasing ionization energy? Upper group is because the shielding effect, electron shielding. You have electron shielding effect decreases. So there's lesser and lesser shielding, meaning that the valence electrons are attracted more strongly. Okay, so make sure we know them. And we also talk about the exception, because I'm looking right here at the exception to ionization energy. It is group 2 to group 3. Case in point here is magnesium to aluminum is your exception. And you can see that exception by looking at the dip. You see that there's a dip right here. Magnesium is higher, aluminum is actually lower. As you go from group 2 to group 3 is an exception to Lewis structure. And also phosphorus to sulfur, so group 5 to group 6 is yet another exception. You just have to memorize those exceptions, okay? So group 5 to group 6, phosphorus to sulfur is also an exception. So if you recall the reason for those exceptions, you just simply write down the electron configuration. For magnesium, you have argon 3s2, so the 3s2. For aluminum, okay, for aluminum, you have 3s2, and then you have 3p1. So what that's saying is that the aluminum has the valence electron removed more easily. So this is lost more easily than expected. The reason you lost more easily than expected is due to shielding, electron shielding. The 3p electrons are more shielded than the 3s electrons for magnesium. Right? So 3p are a little bit further, a little bit more shielded than the 3s electron. And that's why it's lost more easily than predicted. Okay? So that's what this is, right? So this is the periodic trend. But is that what the question is asking? Sorry, I should have read the question first. I forgot to read the question. Let's see what the question is asking, okay? The question says, the first ionization energy is energy required. So it's endothermic. Okay? Ionization is endo, if you flip it, it's exo. So the value of the first ionization energy for the third element, which are these guys, are given. Which of the following is exo? All right. So which of the following is exo? So, well, this is a good question. Okay. So it's a little bit it's a little bit more difficult to use number. What you have here is Hess's law. Okay, because you're seeing ionization energy, and you're also seeing the reverse of ionization energy at play. So that's why I said this is related to Hess's law. So if you look at choice A, for example, you can see chlorine becomes Cl plus. Isn't that ionization energy? That is ionization energy, okay? So I'm looking at here, so I'm gonna zoom this out. You can see that I'm just going to looking at choice A first. So I have Cl becomes Cl plus. This is the ionization energy for chlorine. And the other one, I'm looking at Mg plus to become Mg. This is the flip. This is the negate ionization energy. I got to flip, so I flipped it. The negative ionization energy for Mg. So now you got to look at the chart. How do I know if this overall is endo or is it exo, right? Look at this for a sec. If you look at chlorine, it has an ionization energy up here. So it's about 1250 if you want, okay? So plus 1250. Again, we don't really have to do this, but I just want to show you the reasoning behind it. This is 1250. Look at Mg. Mg is like 750, but you flipped it. Isn't that negative 750 then? Because I flipped, right? So Mg has an ionization energy about 750, flipped it, G plus. So you see the for A is actually positive, which makes it endothermic. Not the answer here. You're looking for which of the following is exothermic. Does that make sense? Yeah. So that's what you do for each analysis. And just for the sake of this, let's look at B. Okay. B is actually our answer. So if you look at B, I'm looking for aluminum first ionization energy. Okay, and I'm looking at aluminum. So aluminum is about a little bit more than 500. Let's call it 600 positive. Okay. Now the second one, you flip Mg. So you look at the ionization energy for Mg and you flip it. So ionization energy for Mg is 750. If you flip it, then it's negative 750. So that gives you the delta H of negative 150, making B the only exothermic one on the list. And you do the same analysis for the other one, okay? So B is the answer. So this one is not asking for the exceptions, but it's asking you to do Hess's law. Number 6 is Hess's law. All right? So number 7. Number 7 is Lewis structure. So you should be very comfortable with Lewis structure. There are like 3 points that you have to take care of, take advantage of, okay? So if you look at the carbons before on the reactant and the carbon on the product, that's essentially what they want you to compare. So this is number 7 now, okay? If you look at the carbon before, what is the hybridization? You look at the electron domain, right? Remember, if you have 2 electron domain, the hybridization is always sp. 3 electron domain, sp2. I'll put it on the side. You have to know how to count something called the electron domain. Single bond, double bond, they all count as 1. As lone pair. Single, double, triple, they all count as 1 electron domain, okay? 1 electron domain. So if you look at the structure here for the carbon, this carbon has 3 electron domain because 1 single bond, 1 single bond, 1 double bond, that's 3 electron domain, that's sp2 hybridized. So do you see that means A and B is wrong? Forget about A and B. And if you look at the carbon after, there's 4 electron domain because there's 4 single bond. That makes the sp2 hybridized. So the answer would be, that makes the sp3 hybridized, I'm sorry. So the answer is D, yeah, for number 7, all right? So make sure you know the electron domain. Memorize that molecular shape chart. I'll put it here. 2 electron domain is sp, 3 is sp2, 4 is sp3, and 5 is sp3d or dsp3, and 6 is d2 sp3. And within each electron domain, there's specific molecular geometry and bond angle you have to memorize. So you got to know that chart to know whether molecule is polar or non-polar. All right. I'm going down the page. Okay. So number 8. Let's look at that. Number 8 is more like an atomic structure. You look at this MgO. Now it's coded for you, but you should know Mg2 plus and O2 minus. Tell me which one is the smaller sphere, which one is the larger sphere? Because both of them have the electron configuration of the neon, right? Again, 2 electron and the loose 2 electrons. So the neon, they're both neon. So you should know that Mg has 12 protons in the nucleus. Oxygen only has 8. So that makes Mg2 plus smaller radius, okay? And oxygen 2 minus is larger radius. So the smaller sphere must be Mg2 plus. And O2 minus is the larger one. So what's the difference here is solid and liquid. Solid, they're fixed together by ionic bond. They're stuck. They can't move. No conducting of electricity possible. In the liquid state, the ions are free to move. So now the liquid, you can see the small circle, Mg2 plus and O2 minus are separated. They're free to move and conduct electricity. So number 8, based on the diagram, which of the following best helps to explain why the solid is not able to conduct electricity, but the liquid is a great conductor of electricity? Number 8 is D, because the solid consists of separate, these one fixed in a lattice, stuck together, but the liquid one, the ions are free to move about, okay? So the answer D, very simple, right? It has nothing to do with free electron. What are they thinking of when they talk about the free electron? If you look at choice A, MgO does not have free electron. Well, free electron has to do with a piece of metal, metallic compound. Metals have free electron. Ionic compound does not, yeah? All right, so the answer is D. So conceptual solids and liquid, okay? Let's look at the next one. This would be number 9. And again, it's kind of a little bit not shaded very well, but the solid shaded one is carbon and the other one is oxygen. So I apologize for this one because it's not, you kind of have to kind of guess a little bit. So let me see, where is my, right here. So right here, I'm going to capture, and I want to capture this question so I can answer the choices here. So I'm looking at the reaction, and the diagram tells you how many of each reactant. That is what the diagram is telling you. So if you look at question number 9, please, here, and you have to count for number 9, okay? So you got to count how many reactants do I have, and how many products can be formed, okay, using the information given. So a mixture of CO gas and O2 gas is given. And the reaction occurs from CO2. So we're told the reaction is CO. Okay. The reaction is CO plus O2 produces CO2. If you balance this, you would have to put 2 here and 2 here to balance. There, that's my balance equation. And if you look at that, if you look at the diagram, now you can count. I see a CO here. This is, I don't want to write on it. I'm just going to circle the CO. So 1, 2, 3. I have 3, 4. This is 4, sorry. So that's why it should be shaded more properly, okay? So I'm going to shade these. These are all CO. So I'm doing a BCA now, because the question says, which of the following diagram, ABCD represent the content of the box after the reaction? Proceed as complete as possible. That means run to completion. So I have 4 CO, and I'm looking at this, I have 3 O2. Okay, so this is, who is limiting then? This is BCA, right? You see the limiting is CO, right here. I have 4 carbon monoxide and I have 3 oxygen. Based on the balanced equation that we have to write ourselves, CO is limiting. So I minus 4 here, and I minus 2 for oxygen. How do I get that? 4 divided by your own coefficient, which is 2. 4 divided by 2 times 1. So you divide your own coefficient times the coefficient of the species that you want. So I minus 4, I minus 2, I plus 4 here. So this would be what I should be seeing. So what am I supposed to see? I will see 1 oxygen and 4 carbon dioxide produced. So which diagram here has 1 oxygen remaining and 4 carbon monoxide produced, right? Do you see that? Okay, so the answer here, I'm looking here is look like it's B, right? You see that B? B has 1, 2, 3, 4 CO2 and 1 O2 in the middle, right? So B is the answer, okay? So this is called stoichiometry BCA with diagram. It's very stupid. They always have a few questions like this on every single test, either equilibrium with diagram or BCA with diagram. Okay, all right, let's look at number data in the set. So you got to be careful here. Data in the set is the hardest, but usually like answer for one part kind of determines answer for the other part. It's annoying in that aspect, but let's take a look at this. Okay, so here I have a reaction. This is a redox reaction. Right away I know it's redox because I have 0 for copper metal and I have copper 2 plus. Oxidation number changed. I know copper metal is oxidized. Okay, Cu is oxidized right away. It has to be redox. Oxidation number change. I have a free element, copper, and I have a copper ion. So I lost electron. So this is an oxidation. And then there's a reduction of nitrogen. Nitrogen is 5 plus here, and nitrogen here in NO2 is 4 plus. So nitrogen is reduced. So right away I know it's redox, okay? And also if you look at this reaction, I produce gas. NO2, guys, every time you see NO2, what pops to mind? NO2, every time you see NO2, Lewis structure, exceptions to Lewis structure should pop to mind. NO2 has 17 odd number electrons. It is also called the smog. So the smog check that we do for our cars, check for the presence of nitrogen dioxide, one of them. So this is also red-orange gas is bad. It causes acid rain, it's an environmental pollutant, and is also acidic, right? Acid rain. So anyway, that's what this is. So the student placed 2 grams of mixture of aluminum and so we have a mixture, 2 grams. The copper will react, I guess, yeah? Is it? Not sure. Okay, but anyways, it says you put in a beaker over the film hood. Why do you need a film hood? Because of NO2. You do not want NO2 to spread in the lab and you breathe in, you're gonna form nitric acid in your lung, right? So no good. So you pour 15.8 molar nitric acid into the beaker. The reaction between copper and nitric acid is represented. The student observed that a brown gas is released, that would be NO2. And the solution turned blue, which is copper 2 plus. Because it's turning blue, I can use spectrophotometer, that Beer's law thingy again. And you can see that, do you see the copper 2 plus concentration is increasing? You went from 0.25 to 50 to 100 to 200, right? So you double every time. But the absorbance does not do that. Something is wrong here about the absorbance. So these two data looks wrong. Looks like they're flipped, right? So if you double the concentration, absorbance should also double, not quadruple. So they must have flipped these two. Okay, one more time. If you look at the concentration for copper 2 plus, it doubled. So this should double. So they must have flipped this. And then it doubles again. So 0.117 double to 0.235. That's okay. And then it doubled again. And 0.235 double to 0.468. Yes. So they flipped these two. Yeah. Okay. That was the problem there. Okay. It doesn't follow the trend. Absorbance should be directly proportional to concentration. You double, absorbance have to double. Alrighty. So number 10, what is true of the reaction? It is not acid and base, so it has to be C or D. It is redox. So they want you to know who's oxidized, who's reduced. Well, C and D both says copper is oxidized, but D is the answer because what is reduced is the nitrogen atom in NO3. It went from 5 plus in nitric acid to 4 plus. So that is reduced. Hydrogen is not reduced. Hydrogen did not change oxidation state before and after. So D is the answer, very easy, right? Okay, so number 10 is D. All right, number 11. If you continue, to determine the number of moles of copper in the mixture, the student measured the absorbance of unknown concentration, copper 2 plus, using a spectrophotometer. The cuvette, which is sample holder, is filled with the solution, and then the data recorded. Which of the following is a possible error? We talked about this, that the error here is when you double the concentration as you go down, the absorbance should double accordingly. So the two sample absorbance must have been switched by error, by accident. Yeah. All right. So the answer for 11 is therefore C. The student labeled cuvette incorrectly, reversing the label on 2 of the solutions. Yeah, 2 of the solutions wrong. Okay, and I've already told you which 2. So 11 is C. Number 12. 2 more questions on this part. Okay. So what is number 12? Let's take a look at that. Student measured that the reaction produced 0.01 mole. Okay, so this is stoichiometry, number 12. If you produce 0.01 mole of copper 2 plus, what percent of copper metal by mass was in the 2-gram sample? Now remember, the original 2 gram is not copper, is not pure copper. It's actually copper plus aluminum. But only the copper reacted with nitric acid and produced your reaction. So you got to go back to the reaction. I need that for stoichiometry, right? So I'm going back to the reaction. Here it is. So the ratio is 4, and then you're going to get CuNO3, blah, blah, blah. I don't care about the rest. So what is important here is I have 0.01 moles of copper nitrate. The question is, how many moles and therefore how many grams is copper? Do you see that? The ratio is 1 to 1. The coefficient happens to be 1 to 1 between copper nitrate and copper metal. So back to the question, you see, the student determined that the reaction produced 0.01 mole. So that's what I got here. So what percent by mass? So if you do the stoichiometry, again, you cannot use calculator. The ratio is 1 to 1. You don't need calculator for this. And you do the molar mass. Molar mass for copper is about 63.5 grams. So this will grams. So it will be 0.635 grams of copper metal. Okay, the 2-gram sample. So now you do a percent by mass. So percent of copper must be 0.635 divided by 2 times 100, and that is basically half of a 0.3 something, right? So isn't that B? 32% is the closest, and there's nothing close enough to this. That's why you don't need a calculator. You could have thought that 0.635 as 0.64 divided by 2. Isn't that 0.32? And 0.32 is 32%, right? Okay, so you can do these comfortably. Reasonably without any calculator. So you cannot use calculator for multiple choice. You have to remember that. You only get the calculator for the free response portion. All right. So number 12 is stoichiometry. So nothing too bad. Let's look at number 13. Okay. Usually these data in a set gets a little bit harder. All right. Let's look at number 13 and see what we want. Number 13. In one student experiment, the reaction proceeded at a much slower rate. So it has to do with kinetics. Rate. How fast, right? So the student, one is very slow. Which of the following could explain the slow rate? All right. So A could not. Because if your metals were smaller pieces, that increases the surface area should be faster. So increase surface area. A should be faster. And B, the student heated the solution. So higher temperature. So increased temperature, rate should be faster. We're looking for the reason why is it slow, right? So the answer, therefore, number 13 is C. Why is C the answer? Because you're using lesser concentration, less reactant, less collision, less product formation. If you use 1.5 instead of 15.8, that is like 10 times, more than 10 times less concentrated. You have much less reactant collision, so you have much less product. So that's the answer, C. Okay? So number 13, common sense. All righty. Let's move on. Number 14, please. So number 14 is different question now. So the student was given a sample of pure white crystalline. Now, when we say something is a crystal or crystalline solid, it tells you very little. So crystals can be ionic. They're crystals. They can be covalent. They can also be metal. So they're useless information, yeah? Like sapphire. Have you guys seen sapphire before? Sapphires are aluminum oxide. Yeah, aluminum oxide are sapphires. So they're ionic. They're crystal looking. Some of them look beautifully Beautiful. So we use them for crystals, right? So sapphires are aluminum oxide. So which of the following would be most useful in providing data to determine whether it's ionic or not? Well, one thing about ionic is that it has high melting point, but covalent too, right? So you want to do C, isn't it? C or D. You want to testing the conductivity. So both C and D conductivity, but not as a crystal. Crystals cannot conduct electricity unless you melt it or dissolve it. So that makes D the best answer. So if in the aqueous form of the substance, you have high conductivity, that would be ionic. Okay? So now the crystal, we already know the crystal form is not going to conduct. So the answer is D for Douglas. All right. Number 15. So if you look at number 15, first thing popped to mind is all of them are nonpolar except the second one. So E is nonpolar. C2H6 hydrocarbons, nonpolar. CH4 hydrocarbon, nonpolar. So all these are London dispersion force, except the second one, HF, is hydrogen bonded, hydrogen bonding. That makes HF highest boiling point. So the answer is B. You don't even need to read the reasoning. Hydrogen bonding. Number 16. So make sure you know that hydrogen bonding is a type of dipole-dipole. It is the strongest dipole-dipole to be considered hydrogen bonding. Your hydrogen must be attached on one end to F, O, or N. That's the first condition. And it has to be bonded to the other side, another F, O, or N, in order for this to be considered hydrogen bonding. So the hydrogen in question must be squeezed between FON on either side to be considered hydrogen bonding. Otherwise, you're dipole-dipole. All right, number 16. Let's look at what kind of question it is. Number 16, a sample of solid labeled as sodium chloride may be impure. All right, so salt. It might have other stuff mixed in them. So the question is that the student analyzed the sample and determined that it has 75% chlorine. And so that would be 25% sodium, right? This is your sample, okay? But what you should have when it's pure sodium chloride, it should be 61% chlorine, and the rest, which is 39% sodium, yeah? This is when it's pure. So the question is, you have too much chlorine, right? So the sample has too much chlorine. So the question is, what could be the impurity here? Is it A, B, C, or D, right? Which one could be the impurity? So if you look at the choices here, obviously it cannot be A, right? If you have only sodium chloride, you should be 61% chlorine, and that is not the case here, right? So you want a sample that elevates, elevates the amount of chlorine. Okay? You do percent by mass, right? Which one will cause the chlorine to go up higher? Now, I am not going to go B because look, why? B, if you look at B, okay, B here, if you look at BCD, what's the difference, right? So we're not going to look at sodium chloride. So we're looking at basically is choice B has iodine, so iodine, and choice C has potassium, and choice D has lithium. So those are the three elements that makes BCD different. And you notice iodine is huge. Iodine has a huge molar mass. So in terms of the molar mass wise, iodine is the greatest, okay? And then potassium, and then lithium. So because they will change the total when you do the percent. So I don't want to add B because adding a whole bunch of iodine, I'm increasing my denominator when I do the percent. That will reduce the overall percentage, not increase. I want one that will increase the chlorine to a higher percentage. Do you see that choice B, by adding iodine, I'm effectively increasing my denominator when I divide to find the percent of chlorine, which means that the chlorine percentage will go down, not up. I want up. And same thing with potassium. Potassium has, so I is greater than sodium, and potassium is also greater than sodium. The only one that produce, it would be the last one, D, because lithium is actually less than sodium in terms of the weight. So that will cause the denominator to shrink, so the percent of chlorine will elevate. And this is why my sample with the elevated percentage should be D. So this is math. It has nothing to do with chemistry. Yeah. All right. So hopefully that's clear. Okay, let's look at number 17. Okay, 17 also, can I use calculator? A pure sample of oxide of sulfur, so that would be sulfur and oxygen. We don't know what the formula is, but it says 40% sulfur, 60% oxygen. So what is the empirical formula? So you could suck it up and do it, or you can kind of look at choice A. What is the percent of sulfur? So choice A. So sulfur is 32, and SO3, right? SO3 would be 32 plus 16 times 3, which is 48. So that would be 32. 32 plus 48, that would be 80. Okay, so is this 40%? Yeah, this happens to be 40%. So I got lucky. I had sucked it up and did the math. I did the sulfur divided by everything. So 17, the answer is A. So that happened to work. So you could do it this way. So you don't really have to do the empirical formula. You could, you get the same answer. So I will just choose A, B, C, D, find the percent of sulfur, and see which one matches 40%. Let's look at number 18. Number 18 has to do with gases, obviously. So if I were to draw this out, I have helium in there. They're all put into a liter, right? So what is the final pressure? So 4 liters of helium, 6 liters of nitrogen, 10 liters of argon. Okay, and I'm gonna put it in here. So this is Boyle's law, P1V1 equal to P2V2, because temperature didn't change; they remained at 0, right? So moles didn't change, so it has to be Boyle's law right here, P1V1, P2V2. So you're gonna do that for each one. So for example, if I start with the helium, initial pressure P1V1, P2V2. Initial pressure for helium is 1. Initial volume is 4. What would be the final pressure if the volume doubled? You see the final pressure would be 0.5. So P2 here would be 0.5 atm. So that means if I were to transfer the 4 liters of helium into a volume that is twice as big, the pressure will go down from 1 to 0.5 atm for helium. Of course, I do the same for the other gases. So I do also P1V1, P2V2 for nitrogen. I had 1 atm, that's what we were told, 6 liters. Now, what is the final pressure for nitrogen? The final volume becomes 8. When I solve for P2, I get 6 over 8. That would be 3/4, 0.75 atm. So that means if I put this 6 liters of nitrogen into this 8 liter final container, my nitrogen will now have a pressure of 0.75 instead of 1. And then lastly is this argon, right? I do another P1V1, P2V2. The initial pressure of argon is 1, we're told. Volume is 10. What is the final pressure when the volume becomes 8? So the final pressure will be 10 over 8, 1.25 atm. So if I put the argon in here, the argon will become 1.25 atm. So now I have the total pressure. This will be the sum of everybody. So the answer is C. The total pressure will be the sum of 0.5, 0.75, 1.25, and that adds up to a total of 2.5 atm. Okay, so that's the answer. So 18 is Boyle's law, before and after question, combined gas law. Doesn't matter how you call it. Okay, the point is before and after type of question. You cannot miss those. Before and after questions are also just free points for you to do. All right, this is the PES spectrum. Okay, photo emission spectrum. So don't forget that, number 19, photo emission spectrum. What the heck is it? It essentially tells you the electron configuration and by pulling electron away. So the general idea is that if you look at the y-axis for these kind of graphs, the y-axis is the number of electrons, right? And the x-axis, if you go to the left, is basically the binding energy or the ionization energy. Okay, similar. to ionization. Technically, they're different, right? Binding energy is just the energy needed to remove electron. Ionization energy only remove the valence. So you're 1, 2, 3, 4, 5, 6. Okay, so you can see that element X, element Y, they're different, right? Okay. So the complete electrons, the complete photoelectron spectrum for two unknown elements, X and Y, are shown. So if you look at element X, is really 1s2, 2s1. So that's lithium right away. And element Y is 1s2, 2s2. So that will be neon. So I'm looking at, not neon, I'm sorry. I mean helium, right? Okay, not neon. All right. So let me go back here. So element X is lithium. 1s2, 2s1. Element Y is helium. 1s2, 2s2. If you look at the periodic table for the relative position, helium is up there. Oh, hold on, that's not helium, it's beryllium. What is wrong with me? Okay, so it's beryllium, okay, not helium. 1s2, 2s2 is beryllium. Okay, Be, yeah. So lithium is down here, beryllium is next to it. So they're in the same period, so beryllium has greater effective nuclear charge and therefore higher valence electron. Okay, so the question is, which of the following can be inferred? Okay, so if you look at A, it has to do with electronegativity. That's not what the PES is telling you. It has nothing to do with electronegativity. It has to do with the energy needed to remove electron. So maybe B and C, because they talk about ionization energy, nuclear charge, right? And it's not D. Isotopes are mass spectrums, not PES. So maybe B and C, if your best guess, right? So is B correct? X has greater ionization energy than Y? No, because Y is further to the right. Y is beryllium. Y has greater ionization energy. So B is fundamentally a false statement, making C the only possible answer. Y has a greater nuclear charge. So does that explain the ionization energy? Yes. Does that mean as so? Yes. Greater nuclear charge means that your 1s electrons are extremely difficult to remove. That's why the binding energy is 12 and 11, where for X is like 5 and 6. Yeah, so it explains both ends. It explains the 1s is high, explains the higher ionization energy compared to X as well. Okay, you see it's not much higher, but nonetheless it is higher. X is only about 0.5, and for Y is like 1. It is higher, right? All right. So PX, make sure you know how to analyze it. It's basically ionization energy, yeah? All right, and the electron configuration. Now, number 20 is intermolecular forces. So understanding who has what. So do you see both of these are polar? How do I know they're polar, guys? Why is compound 1 polar? Because the shape is trigonal pyramid. I don't know if you can see it. It's trigonal pyramid, pyramidal. Pyramidal is always polar. And if you look at compound 2, is also polar. Okay. Even though I have these hydrogen, I have nitrogen here. It's trigonal pyramid as well. It's polar. So trigonal pyramid, and it's also polar. But one of them exhibit hydrogen bonding, one does not. Because if you want to exhibit hydrogen bonding, you got to have hydrogen attached to FON. So compound 2 has 2 hydrogen donors for hydrogen bonding. Compound 1, there is no hydrogen bonding capacity. You don't even have hydrogen attached to FON. All the hydrogens are dead hydrogen that attached to carbons. There's no hydrogen attached to FON. So compound 1 is dipole only. Compound 2 has hydrogen bonding as well. Okay? So the question is, which one should be the higher floating point? You do not want to talk about polarizability because both of them have equal number of carbon, equal number of nitrogen. They have the same molar mass. They're isomers. Are they? Yeah. So this, yeah, they're isomers, right? So forget about polarizability. So the answer must be compound 2. So forget about 1. You know that 2 has hydrogen bonding, so 1 is just wrong. So you have 50% of chance of getting it right. So is it less polarizable? No, they have the same molar mass. If you count them, the molar mass is the same number of carbon, hydrogen, and oxygen. So hydrogen, right? So there's no polarizability differences. So C is wrong. So it has to be the last one by elimination. And compound 2 forms hydrogen bonding. Compound 1 cannot. That's why compound 2 has higher boiling point, intermolecular force, okay? Alrighty. Let's look at the next one. Number 21. 21. Individual question. Based on the molecular structure and bond polarity, which one has the greatest solubility? This is also intermolecular force. Who is the most polar? The answer is C. A and B is nonpolar. We know that right away. You don't have to draw it out. A is tetrahedral, hydrocarbon, nonpolar. B is tetrahedral, nonpolar, right? So both of these are nonpolar, London dispersion. C and D are both polar, but C forms hydrogen bonding, D does not. So this is dipole-dipole only, and this is hydrogen bonding. So who has stronger interaction with water will be the one that dissolves better in water. The stronger the interaction between sodium and solvent, the greater the solubility. So C is the answer. Hydrogen bonding associated with water more strongly than dipole-dipole. So C, ammonia, that exhibit hydrogen bonding will have greater solubility, okay? So that's a very easy question there. Part 22 to 25 is equilibrium. And you can tell it says Kp. So whenever you look at equilibrium constant, in this Kp is 3, right away the first thing popped to your mind, guys, is that this is spontaneous because it's greater than 1. And not only it is spontaneous, it is equilibrium, it is spontaneous, and also involves color change. We already said NO2. If you see NO2, first thing popped to mind is that it is an exception to Lewis structure. It is brown. It is poisonous. It's acidic. All these things should come to mind because that's where the questions come from. And if it's colored, you can monitor the rate by monitoring color change. You can also use Beer's law on this. And Kp means you have to write in terms of pressure, not concentration, because it's Kp. All right, and as reaction progresses to the right, you're going to see darker, darker, darker brown as more brown gases form. All righty, so number 22. The pressure of N2O4 is 1.33. What is the pressure for NO2? That is the understanding of how to write Kp. I'm going to write Kp as products, which is pressure of NO2 squared divided by pressure of N2O4. And 22, just plug it in. So it tells you that Kp is equal to 3, I plug in 3. It tells you N2O4 has a pressure of 1.33. And wouldn't this mean we can solve? So 3, 1.33, and I'm solving for x squared, okay? Isn't that easy? You cross multiply. 3 times 4 over 3 is 4. Put x squared, so x is equal to 2 atm. So the pressure is 2. That's the answer. What pressure? N2O4. No, I mean NO2 is 2. Yeah. You just plug in the equilibrium constant expression, the pressures, solve for whatever you're looking for. That's the answer. So there it is. Yeah. Okay. And number 23. Which of the following helps to explain why the contents of the tube containing the equilibrium mixture turned a lighter color when you place in ice bath? Now, first of all, 2 things here. There's temperature, right? Temperature drop, ice bath. Lighter color means equilibrium must have shifted to the left, right? So that is lighter color. Okay? So lighter color, again, means equilibrium shift to the left. If you shift to the right, you should get browner, right? More brown, darker color. So if you lower the temperature, and this one I always ask students, they still mess this up. This is Le Chatelier principle. If you lower the temperature, you always shift to the exothermic side, period. There's no exception there. If you increase the temperature, you shift to the endothermic side. We are not told is this reaction is endo or exo. But now reading the question number 23, we know that shifting to the left is the exo side. because lowering temperature, putting the ice bath, shifted to the left. So 23, left is exo. Left is exo. So left is exo. You lower the temperature, you shift to the left because the color become lighter. So that means this reaction as written must be endothermic. Does that make sense? You can see the reaction as written must be endo. To the right is endo because left is exo. So this is an endothermic reaction that produces more disorder. How do I know there's more disorder? Because you have one gas on the left, you produce two gases. This is scenario number 3. It is a spontaneous reaction at this temperature because temperature is hot enough, right? We talked about the 4 scenarios, delta G equal to delta H minus T delta S. Scenario number 3 is the endothermic reaction that produces more disorder. So if you're spontaneous, it must be because of delta S, entropy. The entropy, the tendency for the reaction to produce chaos, is what drives the reaction to spontaneity. I know the reaction is spontaneous because the K is greater than 1. And we know this is endo because lower temperature shift the equilibrium to the left. All right? So what are they asking you? If you look at 23, which one is true? Okay. So left is exo. So the answer is B. Left is exo. So B, the forward, is endo. So B is the answer. Okay. So make sure you know how to analyze this, please. Yeah. So just give you one more example of how this is done. I'm going to say that water. Okay, this is the auto dissociation of water. Let's look at this side problem. Okay, so I'm looking at this auto dissociation of water from liquid water into H plus and OH minus. Okay, this is the auto dissociation of water, KW. Okay. Now remember, KW normally is 1 times 10 to the negative 14. Yeah. That is only true at 25 degrees Celsius. So I'm going to say now that in hot water, in 50 degrees Celsius water is acidic. So based on this information only, you should tell me that is this reaction endo or exo? Is the auto dissociation of water endo or exo? This is the given. Given that in a hotter water is actually acidic. Okay, so let's do this together. How do we know this, right? Now, water is neutral. That is only true at 25 degrees Celsius because at 25 degrees Celsius, your H plus and OH minus is 10 to the negative 14. So your X squared is 10 to the negative 14. If you do icebox, X is 10 to the negative 7, which is H plus. And that is why pH is 7. Water is only neutral at 25 degrees Celsius because that's what the equilibrium constant tells us pH is 7. But if it's acidic, that means pH is greater than 7. So you could assume it shifts to the right or left, doesn't matter. Because one way is right, the other way is wrong. So how do you become acidic? Let's say, for example, what if X become 10 to the negative 6? Isn't that pH equal to 6, acidic, right? And if that were the case, if this were the case, what happened to your KW? Your KW would be 1 times 10 to the negative 6 squared, which is 1 times 10 to the negative 12. So it becomes larger, right? At higher temperature. So if your KW becomes larger at higher temperature, that means you must have shifted to the right. You must have shifted to the right. If you increase temperature to 50, you must have shifted to the right because KW increased, because it become more acidic, because pH is 6. So your hydrogen concentration is 10 to the negative 6. So the answer is endo. Yeah, the dissociation of water is endothermic. It takes energy to break apart water into H plus and OH minus. It's endothermic. So if I raise the temperature, equilibrium will shift to the right. If I shift to the right, the KW will increase. Let's say the KW becomes larger, 10 to the negative 12. That makes hydrogen concentration 10 to the negative 6. That makes the pH equal to 6, which makes a solution acidic. So the dissolution of water is endo. Now, let's say we didn't know any of this, and I asked you, is this endo? You should know it's endo because if you flipped it, what are you looking at? If you flip that, you're looking at a strong acid combined with a strong base to form water. Isn't that exothermic? Because neutralization, strong acid and base is always exo. So now you flip it back, the dissociating water into H plus and OH minus, this would be endo. So you should know it from this way as well, right? So either way, you should know which direction is endo and which one is exo. So this would be a Le Chatelier principle. So a little bit harder to kind of get used to. Please memorize the rubrics for Le Chatelier principle, okay? You will need it for sure multiple times on multiple choice as well as on free response. Let's look at 24. So 24, which of the following best predicts how the partial pressure of the species will be affected when you add argon? Well, rubric tells you if you try to increase the pressure by adding noble gases, there will be no shift because that is the wrong way to increase pressure. So the answer will be no change. So the answer is D, yeah? The proper way to increase the pressure is to decrease the volume by compress the container to a smaller volume. And that will cause the pressure to increase, not adding noble gases. All right, number 25 has to do with bond energy. So number 25, we already know the reaction is endo, right? What was the reaction? I forgot. Okay, I think it was N2O4 gas. Dissociate into 2 NO2 gas. We already established that this reaction is written, what did we say? Endo exo, I forgot. Oops, so let me come back here. So this has to be a bond energy question, okay? So we said that this reaction is endo. Okay, we already established this, okay? So to the right is endo. And it produces more disorder. All right. So this has to do with one of the 5 ways to find delta H. We also talked about that delta H of the reaction is the sum of the bonds on the left, which is the bonds broken, right, on the reactant, minus all the bond energies for all the bonds on the right side, in the product side that are formed. This is one of the 3 ways to find delta H when you're given the bond energy. If you know this reaction is endo, then you would argue the bonds on the left side is greater, so the total bond energy on the left side is larger than all the bonds energies added together on the right side. Okay? So we already know it's endo, so A and B cannot be correct, right? So A and B just contradicts this data. So it has to be C or D. Okay, has to be C or D. So how do we know between C and D? You gotta kind of look at your structure, yeah? Okay, so actually you don't need to look at the structure at all. If you look at C and D, one of them is a false statement. We know it takes energy to break bonds. It takes energy to break anything. So wouldn't the C be wrong when it says energy is released when bonds break? That is not true. Energy is required when bonds break, right? So there's nothing you need to analyze further other than that. A and B says they're exo, so that's wrong. We already established is endo. So it has to be D, okay? Now, if you look at this a little bit more in detail, what the heck is going on here is that they actually want you to be able to do, if they give you the bond energy, then you have to be able to draw the Lewis structure for N2O4, which kind of look like this. So N2O4 is this. Now it looks complicated, but it's not. It's 2 NO2 combined. I already told you what NO2 looks like. It's an exception, right? So imagine this. This is NO2. Look, it has 1 lone electron. And here's another NO2, another 1 lone electron. Guess what these 2 lone electrons can do? They can combine. You see, if we combine them, you get N2O4, right? Does that make sense? So what do they talk about breaking bond? This is the bond that's broken, guys. You have to break this bond between 2 nitrogens. Okay, even if you don't know the Lewis structure, you should know that breaking bond takes energy. Breaking bond is endo. So anyway, but if you draw the Lewis structure out, that's what you will be looking for. So the answer is D. Breaking bond requires energy. not the other way. Okay, so 25 is done. All right, so data in the set, we're done with that one. I think we're starting with a new set. 26. 26, let's see, if you can recognize the type of question, that'll be the best, okay? So this is, looks like is Le Chatelier, because we're looking for the reactions are carried out, A, B, C, D, and the question is at equilibrium. Okay, if the volume is reduced, so if you decrease volume means you increase pressure. The rubric I told you is that you shift to the side with lesser gas. We count gases, right? So you shift to the less gas side. Okay, that's what the rubric says. So which one will be the amount of product increased? So if you look at reaction A, I have 5 gases and I have 4 gases. If I increase pressure, it will shift to the right, isn't it? Yeah. If you look at B, I have 1 gas, I have 2 gas. If I increase pressure, I will shift to the left. C, there's 2 gases on either side, so there's no shift. And D, you have 2 on the left, 4 on the right, you'll shift to the left. So A will be the answer, because if you want to increase the product, you have to shift to the right-hand side, and only reaction A shift to the right-hand side, which will get more products. B and D shift to the left, and C does not shift. So this is Le Chatelier. All right? Okay. So don't forget, increase pressure. If you increase pressure by compression, by decreased volume, you'll shift to the side with less gas. Okay? And the opposite is true. Okay? All right. Let's look at 27. Okay, let's see what 27 is. Is the data in the set or what? All right. 27 is solids and liquid. Know what kind of stuff this is, yeah? So I'm looking at steel. Steel is an alloy. Alloy is when you put 2 metals together and you get certain properties, yeah? So carbon and iron makes up steel. Alloys are solutions. They're solid solutions. Solution does not have to be liquid. It can be aqueous. It can be liquid. It can be solid as well. So the data provides some information about 2 types of steel already, both of which are alloy of iron and carbon, which helps to explain that high carbon steel is more rigid. So here's the thing about carbon. Carbon is like rigid. They are not flexible. They are 4 valence electrons. When they're inserted into iron, it prevents iron metals from moving. The atoms can move. So they get stuck in one place. And that's how steel, very, very hard. Iron is bendable. You can bend them with your arm, but you can't bend steel. So we use steel for building material for that reason. So the reason is carbon. Not because it's harder, it doesn't make sense. So A is wrong, right? It has to do with the valence electron and the ability for iron to reduce movement. So A is wrong. C is wrong. It has nothing to do with thermal conductivity. It's just nothing to do with hardness, right? So if you look at 27 then, which one looks like the answer? Yeah. Now B would make it makes them less dense. Wouldn't less dense be less rigid? Dense is hard, right? So that contradicts the data. So even without reading, it's probably D. So additional carbon atom makes it more difficult for iron to slide. Yeah, that increases rigidity if you're unable to slide. When you bend a piece of metal, the atoms have to slide across each other. So D is the answer. Common sense question, yeah? Alrighty. Next one. Okay, let's look at question number 28. We have kinetics because it's fast and slow. Alrighty. So the reaction between NO2 and then CO is given. Okay, the proposed mechanism. So remember, this is super easy. If you want a rate law, you always go after the slow step because the slow step determines the rate. So the rate law depends only on the slow step, not the fast, because no matter how fast you are, you have to wait for the slow step. So you just write down the slow step rate law. And the rate law is always written with respect to the reactant. And the reactant is NO2 again. Look how many times NO2 shows up. And then coefficient becomes power because you're looking at the elementary steps. Coefficient for NO2 is 2. That means it's second order. So the answer is B. There's like no thinking. Is that the rate law always depends on the slow step. Okay. Alrighty. And you cannot have intermediate either. Okay. In the rate law. Rate law can only have reactant. No intermediate, no products. Okay. Let's go to the next one. Next one is also kinetics. So what effect will increasing H plus, that's one of the reactant, have this one? Oh, goodness. I think this is this related to the previous question? Let me see. Sometimes the question off the bat doesn't really make sense. I feel like they might be related. No, there's no H plus, so forget it. All of a sudden just ask me about this, huh? Okay. Okay, so let's look at 29. Okay, 29 is a little weird because I don't know what H plus is. Only catalyst will change activation energy, and I'm trying to find questions that tells me about the role of H plus. It doesn't say H plus is catalyst, so I'm gonna ignore A and B. Activation energy cannot change with temperature. It cannot change by adding reactant. It only changes when catalyst is added. So you have to make sure something is a catalyst before activation energy can change. And we never increase activation energy, right? So we're stupid. All right. So the answer is C. Okay, because the H plus is a reactant. You're basically promoting the collision frequency. By colliding more frequently, rate is faster. So C is the most reasonable answer, right? It has nothing to do with rate constant. Again, rate constant can change with catalyst or temperature. If you increase temperature, the rate constant will increase. Activation energy will not. Okay? Rate constant will increase if you increase temperature. If you add a catalyst, what did I do add a catalyst, guys? If you add a catalyst, rate constant will increase, activation energy will decrease. If you change temperature, if you increase temperature, rate constant increase, activation energy does not change. Okay, only catalyst alters activation energy. Let's look at the next one. So that's kinetic, a weird one for that matter. Oh. Okay, so here's another one. Okay, let's look at this one. What is this question? Okay, so number 30 is a famous equation. It's actually Lewis acid and base reaction. So can you guys memorize this one? When we define acid and base reaction, you don't need to know that fact to answer number 30, but we know that there's different definition of acid and base. Okay, so ammonia is a base because it has an electron donate. Ammonia is a base. Boron is an exception to Lewis structure because only has 6 electrons around the central boron. So in that sense, boron is an electron acceptor, and ammonia is the electron donor. So electron donors are Lewis base. Electron acceptors are Lewis acid. You're looking at acid and base reaction. So what's going to happen is that the lone pair on the base is going to attack the boron. And by forming that bond between nitrogen and boron, you got yourself acid and base reaction. So this is the final product. I don't know why it's in blue, but here it is. And this is the boron. Okay, so that is the final product. They just combine. This is acid and base reaction. So now boron is octet, so is nitrogen. Everybody is happy. Yeah. Okay. So you can see that A and B is wrong because common sense will tell you that hydrogen can never be in the middle because that would require to occupy more than 2. And that's just not allowed for hydrogen. Forget about it. So can you see that the answer has to be the last one? This is actually a Lewis acid and base reaction. Do you need to know this is acid and base? No. But this is what the product that will form. Okay. Alrighty. Next one, I'm looking at G and E. So that will, of course, be thermodynamics. And we should know the formulas. Let's just recap that formula right away. Delta G is negative NF delta E. There, that's the formula. You had to memorize this. Spontaneous reactions, delta E, cell potential must be positive volts. So G will be negative joules. All right? And F is a constant. What about N? N is the moles of electron transferred, right? The common denominator. In this example, you see 2 and 3, my N is right away 6. The common denominator between 2 and 3 will be 6. So your moles of electron transferred right here is going to be 6. Now, how do I know which one to flip? Because you have an issue here. You cannot have 2 reductions, right? They will always give you this in terms of reduction. I know both of these are reduction because electron on the left side. I have to flip this for a galvanic cell. Galvanic cell definition is spontaneous. So there's no other way. There's only one way to flip this to get a spontaneous cell. Which one do I have to flip, guys? I would have to flip the first one in order to have a spontaneous galvanic. So the key word here is galvanic, because galvanic means that the cell potential must be positive. So that means I have to flip the first one. So if you flip the first one, you get positive 2.37. The second one stays as is, negative 0.74. You add them, that's it. Remember, you don't have to times 2 and 3. E will not change anyways. Okay? When you do the Hess's law for cell potential, you can multiply by 2, divide by 2, your E remains the same. So you don't need to times 2 and 3 for E. You just need to know whether you flip it or not. So if I add them, I can't use calculator, right? So this is 1.63. The answer key tells you. So just knowing this will eliminate 2 choices. So you see that it has to be A and B. But to calculate delta G, you got to suck it up and do the math. Okay, so let's suck it up and do the math and see what delta G we get. Delta G equal to negative NF delta E. So N is equal to 6. Between 2 and 3 electrons, N is 6. F is 96485. And we're going to make this about, this is like almost 100,000. 100,000 almost. And E is 1.63. Okay? So what I'm going to do is approximate. That's the only way to do it, right? So if I do, this would be 6 times 100,000 and times another 1.63. I'm going to times 6 and 1.63 because that is 9. Almost like 10. And I have times 100,000. Isn't that a million? So that's 10 to the 6 joules. 10 to the 6 joule will be 100 or 1,000 kilojoules. And that's negative because it's negative. So which one is closest to negative 1,000 kilojoules? The answer is B. You know, it's between A and B. You can guess. You can just guess if you couldn't figure this out. But you get about 1,000,000 joules divided by 1,000, so it's negative 1,000 kilojoules. That would be the closest to B. Yeah. So 31 is Hess's law, is the equation between G and E. Again, if you know G, you know E, vice versa, and you also know equilibrium constant. You just need to know one of those 3. You can find the other 2 mathematically. Okay, they will never conflict with each other. So giving you one information is like giving you the other 2. So make sure we know them. 32 is kinetics. I'm looking at kinetic because I'm looking at catalyst. Okay, here. You see that in the this diagram here, the decomposition of ozone in the upper atmosphere, the potential energy diagram for O3 is present. And you have NO and NO2. So that will be the catalyst. Because in the presence of NO, my activation energy dropped, okay? You see that the activation energy before is greater. And there's no NO. So right here, you see that? This is the activation energy. That is lower, okay? Not much lower, but it is lower. So with NO is lower. And not only is lower, they convert into 2-step. A 1-step reaction now becomes 2-step reaction because you can see the 2 bumps, okay? Anyways, so this makes NO the catalyst. All right. So the question is, Which of the following mechanism for the catalyzed reaction is consistent? Oh, good Lord. Okay. So to figure out which one is the mechanism, you would actually have to check that they add up to the overreaction of the first condition, right? The reaction must add up to the overreaction. And also that the slow step must be the yeah. Excuse me, I need to move this. Oh, this mechanics of moving this around. It's a pain in the butt. Let me move this maybe somewhere here. Okay. Okay, let me capture this for a sec. Which of the following mechanism? Okay, so again, to be the reaction mechanism, you have to satisfy two conditions. The first condition is that they have to, of course, add up to the overall reaction, which is what we are given on the top. And I would assume they all do, because that is the easier definition, right? Okay, so from here, we can do elimination. Again, you always want to eliminate for these chemistry questions so that you can get the right answer, okay? So, number 32, yeah, if you look at choice A, that's not the answer because they don't even add up to the overall reaction. Doesn't make sense, yeah? B adds up to the overall reaction because NO2 cancels, okay? And NO cancels, right? And let me highlight NO because your catalyst have to be canceled in a specific way. Catalyst has to be there on the reactant side in the beginning and has to be there at the end in the product side at the end, yeah? So B looks good. B adds up to the overreaction and it shows NO as a catalyst correctly. So B is the answer. How do you know who's the catalyst? Catalyst has to be put into the right places, yeah? Like this is not a catalyst. C is not a catalyst. C is produced. NO is produced by first, consumed by the second. That makes NO intermediate. So that's not the answer. NO has to be a catalyst. So B is the only possible answer. So that is the answer here. So it looks difficult, but it's not, okay? All right, let's move on. All righty, next one looks like is Le Chatelier, maybe? Yeah, I'm guessing because I'm looking at equilibrium. I'm looking at color. So let's look at number 33. You have this system here, okay? So the equilibrium is represented by this. Initially have equal concentration of both orange and yellow, okay? So again, left side is orange, right side is yellow. Bichromate is orange, chromate is yellow, all right? Which of the following statement correctly predict the result of adding sodium hydroxide? So this is Le Chatelier. If I add sodium hydroxide, what does that do to the reaction, guys? Now you could argue that, oh, sodium hydroxide is not in anywhere, so there's no effect. However, sodium hydroxide, the hydroxide will react with this guy. It's going to react with H3O plus. H3O plus is strong acid. OH minus is strong base. So add hydroxide effectively removes H3O plus. If you take away something, the rubric I gave you, equilibrium will shift to the same side. Taking away H3O plus, hydronium, that's what it's called, hydronium ion. It will shift equilibrium to the same side. It's going to shift to the right. So the entire thing will shift to the right. You're going to be more yellow, less orange. Okay? So what's the answer then? We know it's more yellow, so it's B and C. Now more orange, and will not change, no? Okay? So it's B and C, right? So you're going to shift to the right side, so shift equilibrium towards the product. So how do you know B is wrong for sure? If you look at oxidation number, right? It did become reduced. CR went from 6 plus, sorry. There's no change in oxidation number, right? So when it says reduce CR, it didn't. The oxidation number for CR remained at 6 plus. This is not a redox reaction. So B is wrong if you understand redox. So there's a lot of clue. to answer the question. So eliminate when you're not sure, okay? So the answer is C here for number 33. Let's move on. Let's look at 34, please. Okay. Look like it's the 4 scenarios of delta G, delta H, and delta S. Okay, let's take a look at that. So let me take this out and put it on the board here so we can analyze for ourselves. Okay. Okay. So make sure you understand the 4 different scenarios for delta G, delta H, delta S without numbers. Yeah, it's important that first scenario is when they are always spontaneous. Okay, so this one here. So again, this is number 34 or something. Yeah, 34. So it has to do with delta G equals to delta H minus T delta S. Okay. All right. So, and then, oh, I see what this one is. Let's talk about the solution process. Remember when we say that to dissolve, you have 3 steps. Step 1, you have to break solute-solute. So step 1 is endo, because you have to break the interaction between solute and solute particles. Breaking bond is endo. You also have to break solvent interaction. In this case, it's water. So what is the solvent-solvent interaction? If you try to break apart water as the solvent, you're trying to break hydrogen bond, right? So you got to break solvent-solvent. That means you have to break hydrogen bonding. And your sodium is sodium chloride. So if you try to break sodium chloride, you're trying to break ionic bond. So both 1 and 2 is highly endo, especially breaking ionic bond. But what is the trade-off, right? The trade-off is step 3. Finally, is exo. Step 3 is exo because you're forming the formation of intermolecular force, forming a bond between sodium and solvent, right? Between solute and solvent. In this example, it is ion dipole because you have an ion and a polar molecule. So the ion dipole intermolecular force is exo. When you form ion dipole, it's exo. So if you add step 1, 2, 3 together, that is how you get the heat of the solution. Yeah. So step 1 and step 2, I call them the investment step. It takes energy to break. So 1 and 2 is an investment. And 3 is the payoff, right? So it's the exo. So if you invest more than the payoff, your heat of solution is endo. If you pay off more than your investment, then heat of solution is exothermic. Okay, so that's what they want, okay? So I'm looking at this, this is delta H2 because I'm breaking hydrogen bond. This is delta H1 because I'm breaking covalent bond. And this is the delta H3 because I see ion dipole right here. All these are ion dipole, okay? So number 34, the process of dissolving is represented. Which of the following are the delta H and delta S for each part of the, so each part, okay? So do you see that breaking solvent is endo, right? So breaking solvent is endo, and you breaking apart is more disorder. Right, so the answer has to be A and B. Breaking solute is also endo. They're all endo. So it's A and B. Okay, so between A and B, you have to choose the solute-solvent interaction, yeah? And it's exo already, right? So we know A and B are both exo, so the only difference is delta S. So this is actually a delta S question. When solute and solvent come together, disorder decreases, right? They come together instead of falling apart and become more chaos, right? So it has to be A. So between A and B, the only difference is the last one. Delta S for A is negative. When solute, solvent come together, the disorder must decrease. So that will be the answer there. Okay? All right. Thermodynamics, okay? Next one. I got a bunch of water molecules and hydrogen peroxide. Ooh. This one of those diagramming question again about limiting and stoichiometry is very stupid. Let's take a look at this. Yeah. Okay. This I have a titration. This is a redox titration because it's not acid and base. It is redox reaction. So titration simply means a particular reaction. So you can have a redox titration, no problem. Okay. So our question is that here I have this titration and I have to count it. Okay. I have to count this. Okay. And I need an overall reaction too. So let me transfer this. So this is a good question, guys, because it forces you to understand the definition of equivalence point and half equivalence point. Equivalence point and half equivalence point are not unique terms to acid and base titration. In redox titration, you also have equivalence and half equivalence point. So let me explain what exactly that means first. I can't move this. I don't know why. Okay, I moved it. Okay. Fine. I'm just going to leave it. Okay, so first of all, you have hydrogen peroxide. We're going to count it. How many do you count? 1, 2, 3, 4, 5. I have 10. H2O2. That's it. Okay, so here's the thing. Yeah. So let's spend some quality time on this one because you need to understand it. Yeah. So you have H2O2, and this is titrated with potassium permanganate. All right. So this is what the graph would look like. A titration setup would look like. So tell me, what is in my burette implied? Yeah. So what should be in the burette? Is this purple potassium permanganate? Okay. I am lagging here. So this in the burette, I have potassium permanganate. I don't care about potassium. They're spectator ion. I care about this. Okay. And what is in the beaker on the bottom? I have 10 molecules of H2O2. That is the titration we're talking about. Okay. Now let's understand what equivalence point means. So here's my equation. I'm going to rewrite it. And I don't really care about the rest. Okay. So blah, 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 blah. I don't care about the rest. I care about this. I have 10 H2O2, guys. So here. Let's look at this mole ratio. Do you see the mole ratio is 2 to 5? That's very important. To reach equivalence point, you have to satisfy that 2 to 5 mole ratio. That is what equivalence means. You have to have that specific mole ratio in order to be equivalent. So meaning that, I'm going to take a picture of this so I don't have to write this again. Yeah. So let's look at this example. What is an equivalence point? Okay, so I'm going to come back to this. Right now, I just want to discuss what is the equivalence point. What is half equivalence point? Okay, so this one here first. This is my 2 to 5 ratio. I'm going to get another one now. One of them is going to be our equivalence point. One of them is going to be our half equivalence point. What's the difference? Okay. So here it is. So if I have 10 of those, my equivalence point, this is that equivalence, okay? How many do you need for MnO4? You look at the ratio. You see it's 4. You need 4 to reach equivalence point. But if you are half equivalence point and you have 10, you need to reach half. So you only need how much to become half equivalent? You only need 2. Okay, so let me take out this 10 here. And do you guys see how I got 4? I need 4 to reach equivalence point because that's the mole ratio. So you given 10, given 10 H2O2, I need 4 MnO4 to reach equivalent because of the mole ratio, right? So if I erase all this, if I'm given 10, how do I find out how much do I need to become equivalent? 10 divided by 5 times 2. So I need 4 MnO4 minus to reach equivalent. Right? So half equivalence will be half of that. So that means I need 2 MnO4 minus to reach half equivalence. Okay? So that's what that means. Right? So let's take a look at the difference here. So we're going to do BCA now. Okay, so I'm going to write the equation again here. And here's another equation. So again, I'm going to do BCA, one for the equivalence point and see what I have left after the reaction goes to completion. And the other one is I'm going to do a BCA for the half equivalence point and see what exactly I have left. Okay, like that. So maybe I should have written the products, huh? Great, but yeah, let me write in the products, okay? So I have 6H plus, and I have 2Mn2 plus, 5O2, and A water. So, because I'm doing BCA, I best write it in, right? So let's go back to the equivalence point, okay? So the top one is going to be the equivalence point, and the bottom one is going to be our half equivalence point later, okay? So let me put it somewhere else, okay? So here's my equivalence point. I know I have 10, I have to add 4. And I don't care about the other reactant. I assume they're enough of them. So this is 0, 0, 0. So if you minus 4, you minus 10. That's what equivalence means. Equivalent means that you have no more left. That's what equivalence means, okay? So so this is equivalence point. We added the equivalent amount after there's none left. That's what equivalent means. Okay, so then what do you have to plus here? I would have to plus 4, I would have to plus 10, and this will be plus 10 divided by 5 times A is 16. So this will be 4, 10, and 16. So this is what I have left, okay? This is the equivalent. What about half equivalence? So let's do a half equivalence, BCA. Okay? So I'm going to do a little bit down here. So the only difference between equivalence and half equivalence is half equivalence, instead of adding 4, how much do you add? You add 2. Everything else is the same. So you can see that I'm going to write the full equation now. This will be 6H plus, I have 2Mn2 plus, I have 5O2, I have A water. So I'm attempting this now at half equivalence point. So I have to add 2 for BCA. This is still 10, okay? But because I'm half equivalence, I add half as much as I need to become equivalent. So this is 0, 0, 0. So you do the same. If you minus 2, I have to minus what? 5. So that's what half equivalence is. And then I would plus 2, plus 5, and then plus 8. So I would have some hydrogen peroxide left at half equivalence point, yeah? So let's see what the question wants. Does the question want equivalence, or does they want a half equivalence? So you just look at what the question wants, okay? So if you look at this one, which of the following, if you read the question now, okay? Which of the following particle diagram is halfway to the equivalence? And they're saying that water and H plus is not shown. Sure, I don't want to see it. So I'm looking for the half equivalent. I'm looking for this one here, half equivalence. So I'm looking for a diagram that has these and this, right? There's no water shown. I don't want to show water, right? Okay. And then and oxygen gets bubbled off. So what am I looking for? Okay, I'm looking for that. So which diagram is this one, right? So if you look at diagram is C. Look what diagram C has. How much H2O2 do you have? If you look at C, isn't it 5 H2O2? And that's exactly what we expected. And how many Mn2 plus? I have 2 Mn2 plus. Isn't that what this is? Mn2 plus, you produce 2 of them, right? And oxygen is bubbled off, so it's not going to be in the solution, and water is not shown. And hydrogen, it's not shown either. We don't care about those. So you're going to see the best answer. Okay. Now, Do you understand this? Now can you tell me which one is my equivalence point diagram then? Because if I were the test maker, I'll put an equivalence point. So equivalence point, I have none. I have no more, anything. I just have an Mn2 plus. Do I have them? No, I don't have equivalence one. But if I had drawn an equivalence one, then I will have no more H2O2, no more MnO4. I will have 4 Mn2 plus. So the equivalence point diagram will be quite boring. In fact, the equivalence point diagram would only be 4 Mn2 plus left and nothing else. This would be at equivalence point, okay? So this is called titration. So equivalence point is not just for acid and base. Equivalence means you have equal mole ratio. So both reactant will be consumed completely against each other. They're equivalent according to the mole ratio, 2 to 5 in this case. That's what equivalence point means. Okay, let's look at the last set. Okay, so I spent a little bit more time on that one than I want to. Okay, so let's look at this one. So this is the bond energy one we talked about, and you can see that this is never spontaneous. Why? Because H is positive, S is negative, G is always positive, never spontaneous. So the question here, which of the following temperature condition is favors thermodynamically? So never, because it's never spontaneous. So the answer is not favored at any temperature. Okay, so this is a second scenario. G is always non-spontaneous. Number 38. If it's non-spontaneous, equilibrium constant will be less than 1. It's not spontaneous, right? So A is wrong, B is the answer. So like super easy. You just did 2 questions without any thinking, right? Okay, so you just know that this is scenario number 2, never spontaneous, and not spontaneous means K is less than 1. So B is the only possible answer. Okay, K can be negative, right? All right, that's it. Alrighty, now the bond energy. This is the annoying part because you got to use bond energy. You got to use all the bonds on the left minus all the bonds on the right. And that will equal to 12. That's the delta H. So a lot of the bonds repeat, that's the thing. So you could potentially do this question by looking what bonds don't repeat. So they don't have to give you a bunch of data points. They just want you to figure out, okay, so here, okay, which one repeat, which one does not. So if you look at this question number 37, and I have the equation here, I just want to focus on the new bonds, not the repetitive one. But I still have to tally them up, right? Because that's the only way I can tell which bonds are broken and formed. So the formula says, okay, the question asks you, which is the closest energy to Cn? So yeah, this is the bond energy one. So you have to use delta H for the reaction. It's all the bonds on the left minus the sum of the bonds on the right. Okay? So I'm only going to highlight the differences. So all the bonds on the left, I have this OH. You see that? Okay, I'm going to highlight this one. So it's still lagging. I can't highlight this. So there. So OH here. Okay. And then this one does not. And I also have this one. So I'm highlighting all the bonds that I care about. So let me because everything else repeats. Yikes. This is lagging not a little bit. It's so stupid here. Okay. Let me just use another. Okay, I don't want to use another one. So bonds broken. So I also have bonds broken here. This bond is broken. And what are the bonds formed? So the bonds formed, I'm going to use a different highlight. I form a new bond right here, which is between C and N. That's bonds formed, okay? And I also formed H2O, right? This was not there. So like that, okay? So that's what I focus on. Everything else is repeating. So when I tally up my delta H, and I know the delta H is given. The delta H is given here, 12. You see the 12 kilojoules. So I know the delta H is already positive 12. Now my goal is to figure out how many bonds on the left and how many bonds on the right. I got to subtract them. So all the bonds on the left, okay, still lagging, minus all the bonds on the right. So bonds on the left, they repeat. So the new one is C and O, and also O and H, minus and also N and H. Yeah, those are the new ones. Everything else repeat. Minus all the bonds on the right, and one more, I have NH also. So 1, 2, 3. Okay, and all the bonds on the right, I have what? What are the new bonds that are formed on the right-hand side? So it's in green, right? So I have the CN bond, and I have OH2 of them. There. Everything else cancels out. I don't need to include them in my summations. So the left side, everything repeats with the right side, except the CO, OH, and NH here. And on the right side, these are the ones that are formed. So now I just plug it in. I can solve for it. That's why they give you some of those bonds. They're kind of weird why they give you all those, because they want you to plug it in and solve something. So let's look at CO. CO is 360. NH is 390. OH is 460. So I add them. Minus the bonds on the right. We're looking for CN. So CN is your X. And 2OH, what is OH? Is 460. There, I have a math equation I can solve for X. So 12 is equal to, now 360 plus 390, that is 750, right? 750, that would be 1210. Minus, and this is 460 times 2 is 920, right? So you can suck it up and do this, right? And you approximately, right? So there it is, yeah. So this is 12. This is 1210 minus X minus 920. Now 1210 and 12 cancels about negative 1200. 12 is like 10. You might as well say this is about 10. And that would be minus X minus 920. So X would be 1200 minus 920. And that is closest to 300. Right? 280, right? So about 300. So the best answer is B. So 37 is B. So a question like this, if you really get stuck, this is not the one you want to spend 10 minutes on. One is to move on first, but you know it has to do about energy, so that's what you look after. Okay, look after. Okay, number 39. 3 saturated solution XYZ. Which one has greatest Ag? So you solve for it. They all have 2 ions. So for X is 5 times 10 to the negative 13 is equal to X squared. So for X, and you do the same for everything. They all equal to X squared. For Y, it's 1.8, 10 to the negative 10 equal to X squared. And for Z is 8.3, 10 to the negative 17 equal to X squared. So which one has the biggest? Of course, we add Y. So easy. Y, then, okay. Will be the biggest. This is negative 13, I'm sorry. So Y is the biggest, I said it wrong. And then X, right? And then Z. Okay, so this is easy. Just solve for X. Molar solubility. That's what X is called. Next one here. Looks like a calorimetry. So when 50 grams of this added to this, temperature drops. So this is endothermic. Okay. But now what if you add it to 1,000 instead of this, right? Approximately how much? Okay, so you can do proportion here, or you can calculate this. So the change in temperature is 3 degrees Celsius if you put into 100 mil. What will be the change in temperature, right? For the same reaction, but now you put it into 1,000 mil, right? So the change in heat is the same because you both put down 5 grams. So Q is the same. So if you look at Q equal to MC delta T, MC delta T, right? So delta T here is 3 degrees. Q is the same. So what if you 10 times the mass? With the same Q, your drop in temperature must go down by 10 times in order to have constant Q. Does that make sense? Your mass increased by 10 times, 10x. your change in temperature must decrease by 10x also. So the change in temperature 3 will be 0.3. So the new change in temperature will be 0.3, the 10 times less than the change in temperature before. Because now you have to absorb 10 times as much heat from 1000 instead of from 100. So the initial temperature is 25. It becomes cooler by 0.3 degrees because the temperature dropped. So your final temperature is 24.7. So the answer is B. Number 40 is B. Proportion, there's no calculation there. Yeah. Okay, the same amount of heat must be absorbed now from 1000 mil, means that your temperature must be dropped by 10 times less. Number 31 looks like it's a Q versus K. So I just had to find Q. Number 41. How do I find Q? You first write down the equation first. So it will be concentration of O3 squared, concentration of O2 third power. Find out what Q is. So plug it in. So my Q, O3 is 2.5 squared, and O3 is 0.15 cubed. Okay. You see this without calculation is great, is huge, much greater than your equilibrium constant. Equilibrium constant is like 10 to negative 15, 56. You don't need to calculate this. You'll be sitting there calculating, you'll be wasting time, right? This has to be bigger. So if Q is bigger than equilibrium constant, equilibrium will always shift to the left, follow the inequality. It's going to shift to the left, okay? So you can eliminate the choices, so it has to be C and D, because only C and DQ is bigger. And if you shift to the left, what happened to O3? O3 will decrease. So D is the answer. If you shift to the left, O3 goes down. Q is bigger than K. That's it. That's the answer. Okay? That'll be the answer. So D is the answer. Let's look at the next one, 42. Okay. So this one looks like Kp right away is huge, so spontaneous. I have 3 steps, and I have delta H's. Step 1 is the slow step. Okay? That's why that is number 42. Which of the following identify the greatest single reason Kp is overreaction is such big? So why is so spontaneous? They're asking. Yeah. So spontaneity has nothing to do with activation energy. So A and B is just wrong. Activation energy has to do with speed, not spontaneity. So look at the equation here. This one is thermodynamics. Okay. So you see that here, delta S is two gases. So delta S is approximately 0. Your delta H for the reaction, you got to add them. You see 242 plus 4 minus 432 is negative. So this is an exothermic reaction that has approximately 0 for S. So what is the reason for spontaneity? Must be delta H. Delta H is very negative. Delta H is the driving force for spontaneity here. Not S, S is 0, right? You want positive S, you want negative H. So delta H is the reason that the reaction is highly spontaneous. K is huge. It's because of delta H. That's the driving force. So that's the answer. And you can eliminate this because it has nothing to do with activation energy. And S, you don't know if it's positive. It's 2 versus 2, right? So the answer must be D. H is huge negative. That's what makes G negative. That's what makes equilibrium constant huge. All right, let's look at the next one. Next one, number 43, you got to add up the delta H by hand. So we just have to suck it up and do this. I'm not going to because I'm running out of time. We're just going to add up on calculator. So that's the delta H, and then you just divide it by how many moles of HCl. You got to divide by 2 because you have 2 moles of HCl, yeah? So if you add this together, you got 242 plus 4 minus 432 is negative 186. That's the delta H for the reaction, negative. But it's for 2 moles, so you got to divide by 2. So the answer will be A, negative 93, okay? Don't forget to divide it by 2. All right. That's that one. And then 44, the compound is not flammable. So again, CCl4 is nonpolar. So basis of periodic property, which one is right? So you're looking for something similar to this, will be C. Okay, carbon with 4 halogen. You don't want to put B. B is methane gas, is highly flammable. So the only one that's tetrahedral, the only one that has carbon with 4 halogen is C. So common sense question, yeah? So it's just looking for pattern here. All right, next one. We have, this one is Hess's law using equilibrium constant. Remember, if you add, you got to multiply equilibrium constant. If you flip, you reciprocal, right? So if you look at this one, the first one stays as is, and the second one has carbonate. So I have to flip the second one, and the third one, oh, I can't tell that one, I'm sorry. Okay, so you got to do Hess's law on this, I'm sorry, yeah? So, yeah, you want to cancel this. So the second one I have to flip. Okay, I have to flip the second one because I'm looking at carbonate, okay? All right, and then if you look at, so if I flip the second one, hydrogen is on the other side. Okay, so it's on the left side, that will cancel, okay? Then the other one is keep as is, right? So 45 is, yeah, is D, right? Okay, so the other one you stay, yeah, you don't do anything. And that Hess's law will work out. So the first one you stay, the last one you stay, the second one you flip, they will add up to the overall reaction. And that's why if you add them, you got to multiply K1 and KW, and you flip this one, so it becomes reciprocal. So the Ka has to be on the bottom. So the final equilibrium constant is D. This is Hess's law. Okay, Hess's law. Alrighty. Give me one more sec. Almost there. Okay, so this one equilibrium constant is less than 1, so equilibrium favors the left. So less than 1 means equilibrium favors left. Now there's 2 acid and bases here. This is the acid. This is the conjugate base. This is the acid. This is the conjugate base. If you shift to the left, that means the right side are stronger acid and bases because they push equilibrium towards left. So the right side is stronger. Okay, so the answer for 46 is D. The right side acid is stronger and the right side base is stronger. Yeah. So if you shift equilibrium to the left, the right side acid and bases are stronger. I know we shift to the left because equilibrium constant is less than 1. Okay, so know these questions. All right. Next one is also Hess's law. Okay, so you just have to figure out what to do with these 2 equilibrium. I want Ag on the left, so this one stays, and I want this on the right, so this stays. I just add them. If I add them, I will multiply it. So if I multiply them together, the equilibrium is 16 times 10 to the 6. Okay, so 47, the answer is C. Right, so equilibrium constant is 16 times 10 to the negative 6, which is 1.6 10 to the negative 7. And it's huge, so that means you're going to get a lot of products, right? All right, lots of products. All right, so this is Hess's law as well. The first one stays, second one stays, I just add them to get the overall reaction. So you see how many Hess's law they like to do, equilibrium, so it showed up quite a bit, right? Okay. The other one here, let's just go over this another time. It's similar. This is Hess's law. This is stoichiometry, titration, easy ones. Okay, they're not hard. Okay, they're not hard. So we'll look at these 3 next time. I think we have time to finish. I spent too much time earlier. All right, so we'll stop here. I'll post this on, and please do the questions and for the office. Okay, guys. Thank you, guys. I'll see you guys later. Bye, guys, on the online. Bye, guys. Bye, online students.